All right. Good afternoon, everyone. Can one of you please confirm that I'm audible?
Yes, you're audible.
Yep. Thank you. All right. So, welcome everyone to this course on information theory. This is the course code is EE5847 or EE2340, depending on which one you've registered for. So in this course, we'll be talking about the basics of information theory, and this is sort of, and after this, there will be follow-up courses, two other courses, source coding and channel coding, that I will talk about in a short while. Uh, so so we'll begin, since this is the first class, we'll have I'll discuss the logistics of this course, and then sort of get into the introduction, and then we'll dive into the details. Okay, so I am the course instructor for this course. My name is Shashank. My office is in academic block C, room number 214D. And the lectures will be held in this slot. So the timetable slot is E. And if you're having classes in person, then this will be in ALH1. Otherwise, we'll be having it on Google Meet using the same link that we're using today. And so we'll experiment with a hybrid class. Definitely. So if possible, I would like to take classes in person. But on the other hand, if any of you face any kind of symptoms like cough or cold, I would encourage you to attend this from online. But please do inform me in advance if you would like to attend the class online. Attendance is mandatory, either offline or online. And as we'll see, there is a part of your grade comes from class participation. So I do encourage, I want an interactive class, so you should participate in class discussions as much as possible. So there is a course web page. So you can just go to my website and then go to teaching and look at EE5847. So I can just go to my homepage, which you can also access from the EE website, and then go to teaching and information sciences or information theory, Jan to April 2022. And most of the course information is available on this website. I'll also provide a link in the Google Classroom. So this has a bunch of details, including assessment and class timings, the tentative syllabus, textbooks and references, and tentative schedule, sort of the high-level overview of what topics we will cover in this particular course. Note that this is a one-credit course, so we'll be ending in segment 2, and notes, materials, and homeworks will also be posted here. All right, so I'll let you know every time I post something, some sort of notes, but do check this page periodically for any information. So, all right, so the assessment will be based on multiple things. So you're all expected to, of course, attend class regularly and participate in class discussions. There will be homeworks, quizzes, and there will be a final exam. Right. So the homeworks will carry around 40% of the grade. Now this is slightly subject to change depending on how things goes. So maybe 5% here or there, things might change. But overall, we will follow this assessment scheme. So there'll be 2 to 3 homeworks, and this will be 40%. So you'll have short quizzes in class, which will count to around 20% of the grade. Your class participation and attendance will account for 10%, and the final exam will have roughly 30% of the grade. All right, so yeah. So one point here is that please try to join using your IITH email IDs, because then you can directly join without me having to let you in. Okay, so this is one credit course in segments 1 and 2, information theory. If you're interested in getting to know more of the details, we have 2 other follow-up courses, source coding and channel coding, which I will be teaching in segments 3, 4 and segments 5, 6. Some of you may have already registered for this course, but the registration will also be open later on. So these 3 courses put together generally constitute a standard information theory course in most places. So the first 2 segments will cover some of the basics, which is necessary. Segments 3, 4, which is on source coding, will cover the details of data compression, and segments 5, 6 will talk about channel coding, or sometimes error correcting codes for noisy channels. And we'll loosely follow. There is no fixed textbook for this course. I'll provide lecture notes and other material, but broadly speaking, we'll follow as references. You can use the following 2 textbooks. One is Elements of Information Theory by Thomas Cover and Joy Thomas. This book over here, and the other textbook is Information Theory, Inference and Learning Algorithms. These are both great textbooks, but we'll take topics from both, but we won't follow it exactly. Okay, but I'll point to sort of general sections which you can go through for specific classes. Both textbooks are available in the IITH library, so you can take hard copies from the library. The second book is also available for free online. You can get a PDF. You can download a PDF copy for free from the author's website. So just Google for information theory, inference and learning algorithms, and you should be able to access a PDF copy of this book. All right. So as I mentioned, the evaluation will involve assignments, exams, and quizzes. For assignments, you're allowed to discuss with each other, but you should hand in your own copy. Copying is strictly not allowed. You can discuss the ideas behind solving problems or assignments, but you're not strictly, you have to write the assignment in your own words. And so assignments will involve both mathematical problem solving as well as programming. So you're free to use any one of these 4 languages to hand in your programming assignments. I would prefer that these be handed in C, C++, or Python, but you're also, if you're not comfortable at all with any of these 3, you can use MATLAB. There'll be 2 or 3 assignments in this entire course. And as I mentioned, most of the weightage will be for assignments. So around 40% of the weightage will be for assignments. There will be one final exam where of course no collaboration is allowed. This will be in person at the every end of the course. And during the course, we'll also have short quizzes in class. These may range from 5-minute quizzes to maybe around 15-minute quizzes. So we'll have some in between, and they'll be very simple and mainly to test your understanding up to that point. It's always good to be up to date so that you can follow everything in class, right? So also sometimes in between I ask some bonus questions, and if you answer a bonus question correctly, if you're the first person to give a bonus to give an answer to the bonus question, then you'll get extra points. So this is in addition to whatever is allotted for these. And anyway, it is to be understood, and but I'd still like to emphasize that any sort of malpractice, any kind of cheating in exams or quizzes or assignments will be severely penalized. Okay, and so that's regarding evaluation. And I am assuming that you have the following background. You should know, you should be comfortable with some level of programming. I don't require you to know too much. You don't have to be an expert, but at least basic programming in one of these four languages is required. If you have taken the digital communications course, it's good, but it's definitely not essential. And the main reason why we'll use digital communication is just to motivate some of the problems. But even if you have not taken a course in digital communications, that's perfectly fine. You will be able to follow the entire course. What is essential is that you know a fair bit of probability. So some basic concepts in probability will be sufficient. Maybe a 2-credit course on probability should be enough. In particular, you should know what random variables are, continuous random variables, discrete random variables, what is a CDF, what is a PDF, what is a PMF, and you should at least be familiar with some basic distributions, Bernoulli random variables, binomial, Gaussian, and exponential. We mainly use these four distributions in most of the course. And you should know what expectation is, how do you compute the mean, variance, and moments and moment generating function for random variables. You should be comfortable with the definitions of these concepts and how to solve basic problems. Nothing too advanced is required. You should know what independent events are and what is Bayes' theorem. So it's a good idea to refresh your probability concepts. You can use whatever textbook or lecture notes you had in your probability course, or these two textbooks are pretty good, by Papolis or Sheldon Ross. Both are extremely good books, so it's always good to refresh these concepts. We will use a lot of probability in this course, so make sure that you revise those concepts. I will be introducing some basic concepts, but I will assume that these you are fully comfortable with these concepts mentioned over here. Okay, so any questions? At any point, please feel free to unmute yourself and ask questions. You can also put your questions in the chat box, but it's always helpful if you just unmute yourself and ask, because I may not always be monitoring the chat box. Okay, I want this class to be as interactive as possible, so please do ask questions. So any questions regarding the logistics or evaluation or background?
Sir, it's going to be only today's class is online, or?
So this week we'll have it online. So today and tomorrow. From Monday onwards, we'll try to have it offline.
Okay, thank you.
Any other questions? So I have sent you all an invite for the Google Classroom. So in case you have not received the invitation, or in case you've not or you've not joined or accepted the invitation, please do so, because most of from now onwards, all the announcements will be made in the Google Classroom. So please do monitor this for announcements and other for material and assignments and everything else. Okay, so if there are no questions, then let's get started. Okay, so why study this course? We're studying a course on information theory. How is it relevant to to whatever you are studying? You may be doing a BTech or MTech in electrical engineering or computer science or computing. So some of you may have taken this because it's a core course. Some of you may just be interested in exploring, or you may have some other motivations for taking this course. But this course on information theory is rather foundational, and that is because it deals with information processing, which we deal with in many other problems and in many other fields. And in fact, the concepts of information theory form the foundations of many other fields, including digital communications, in data storage and processing, in statistics and machine learning, in security, and in fact, even areas such as physics and neuroscience. So in digital communications, information theory basically tells you how do you communicate reliably from one point to another. If there are multiple users who are trying to communicate, take a typical cellular communication system, then what are the fundamental limits of communication? So what is the maximum amount of information, whatever that means? What is the maximum amount of information that can be sent to multiple users or from multiple users to other users? Right? And we will discuss this in some detail in this course and in the follow-up courses. It's also used a lot in data storage. So in particular, how do you compress a file? And given a particular file, what is the minimum file size or minimum compressed file size that you can achieve? Is there such a limit, or if so, then what is that limit, and how small can a compressed file be? So concepts of information theory are used a lot in statistics and machine learning, and in fact, so if you've done any sort of a machine learning course before, then one very common loss function which is used is the Jensen-Shannon divergence, which is a very basic information theoretic quantity. In fact, it's derived from another information theoretic quantity called the KL divergence, which we will study a lot in this particular course. And it's also used in security. In fact, one of the very early papers on security was by Claude Shannon, where he formally defined what it means for a communication system to be secure. So information theory covers the basics of, or the basic principles, governs the basic principles of many of these fields. There's also a very deep connection to physics. In fact, I'll introduce a term called the entropy of a particular random variable. And this term entropy, in fact, comes from physics, from thermodynamics to be precise, where you have the same expression for entropy. And in fact, there's a very deep connection between information theory and thermodynamics. So if you're interested, you should look up this particular term called Maxwell's demon. So just Google this term, Maxwell's demon. It's a very interesting concept. It's a thought experiment, and in fact, this in some sense gives a connection between information theory and thermodynamics, to see that information and the concept of entropy in thermodynamics are in fact very deeply connected. It's also used, information theory is also used a lot in neuroscience, computational neuroscience. So one question that many neuroscientists have been looking at is how much information does one neuron pass to the other? After all, what is being sent through a neural system are electrical signals, and of course these are just simple electrical signals, but how much of that is useful information, and what kind of information is being transmitted? So in this course, we won't be talking about the qualitative aspects of information. We don't really care what it means, but what we're interested specifically is in quantifying the amount of information. So we'll begin with a very loose sort of conceptualization of what information means. We'll try to see what does it mean for something to be more informative than another, and then I'll give a more formal definition for information, and that will be tied to a very specific problem, and the notion of information will arise as so it will give an operational meaning to what we understand about information. Okay. So let's start by trying to understand what exactly we mean by information. Suppose that I wanted to measure information in some fashion. Okay. So how do I measure information? But what does it mean for something to be more informative than another? Right. So let's say that I tell you something. For example, this course. If you knew all of this beforehand, then what I'm telling you doesn't really convey much information, right? So when you say that you're getting some information from me, it means that you're learning something new, something that you did not know before, right? So for example, let's say that I'm tossing a coin. Okay. Now a priori, you know that if I toss a coin, then it can land either heads or tails, right? But a priori, you don't know what the outcome will be. So you know that it's either going to be a head or a tail, but then there's a 50-50% chance of it being either a head or a tail. Now, after I toss it and tell you that it's a head, you've got some information. You've got some. I'm giving you information about the outcome of that particular event. All right, and this is what I say when I say that I've given you some information. So you've got information by seeing the outcome of this random experiment. Okay, so let's try to at least qualitatively understand what it means for something to be more informative than another. Okay, so let's take two examples. One is I toss a coin and I tell you the outcome of that, right? It's a head or a tail. Then another experiment is that I roll a die. Right? It's a 6-sided die. I roll it and I tell you what is the face which comes on top. So it's a 1, 2, 3, 4, 5, or 6. Correct? So these are two different experiments. But out of these two experiments, which one do you think gives you more information? Any guesses? Anyone? Just take a guess.
So can you repeat? I couldn't able to understand if you can repeat.
Okay. So you understand what I mean by information, right? So let's say that, okay, intuitively, I have two different experiments. One experiment is I toss a fair coin and I tell you whether the outcome is a head or a tail. Okay, so head or tail. Now, if I roll a die, then the face, I roll a die and I see which face comes up on top. So it can be 1, 2, 3, 4, 5, or 6. Right? There are 6 outcomes to this particular experiment. And when you see the outcome of this experiment, you get some information. I'm saying that you get some information. So if you had to take a wild guess as to which of these two experiments gave you more information, what would you say? Do you think that the outcome of a fair die gives you more information than the outcome of a fair coin, or the other way around?
Fair die.
Both of them was the same. Both of them are like kind of same, right? Because the context is different in the cases.
That's perfect. Okay, that's fine. So we have one example that both of them give you the same amount of information. because okay, because you didn't know, because you don't know which one you might be more interested in, right? Okay. Any other answers?
Sir,
Yes.
I don't know if it's right, but fair die.
Mhm.
Here we have like six different outcomes, like,
Okay.
and in a coin it's only two.
Okay.
So I mean, in the sense like in the first case it can be head or tail is like it is like we know to some extent. I mean, I understand it's a random experiment,
Okay.
but
Okay.
the information we get is like either head or tail. But
Mhm.
in a die, the, the outcome is it's more diverse in the sense like
Okay.
there's more variety. So
Mhm.
maybe it's more informative. Uh,
Okay.
Maybe I
Fine.
just think that.
Okay, so this is one answer, and that is that the fair die gives you more information than tossing a fair coin. Okay, fine. Any other answers?
Sir, I think it's a fair coin
Okay, a
because
fair coin gives you more information. Okay, why do you say that?
uh, for one event, like if we toss a coin,
Okay.
uh, it either comes the heads or tails.
Mm-hmm.
So we can also understand that the other, I mean, the bottom, like which is like if it is heads, we know that it is not tails.
Okay.
Whereas in dice,
Okay.
if we get like if we roll the die,
Mm-hmm.
we'll get one of those six,
Okay.
but we cannot tell about the others, right? Which is on the bottom, which is like on the left
Okay.
or right.
Okay. So one argument is that okay. So if I tell you that it's a head, then you know that it is not a tail. But then if I tell you that it's a one, then then you know that it is not two, three, four, five, or six, right? So what I'm interested in is the top face, right?
Yes.
And that is, you know,
But
that is one.
but the rest of the information we will not be able to
Okay, what do you think the rest of the information is?
like the bottom number or the sides.
Okay, so you don't know the side numbers. You know the bottom
Yeah.
number because the die is typically, if you know the top, you know the
Sides.
bottom. But sure, okay, you don't know what is the orientation of the sides. Okay, fair point. Okay, so good. I mean, there is again, there is no one way to define what information is, right? So it's a very loose concept, and in some sense, sure, all of you could be right. That all of you have very fair points, but now let me give some more context to the problem. Now, let us say that now I have these two experiments, right? Now, out of these two experiments, let's say that I cannot. So, suppose I want to convey the outcome of the experiment to you, but how do I convey the outcome of the experiment? I convey it using, let's say, bits. Okay, I want to encode the output of or the outcome uh, of of the experiment, but then I'm going to convey the outcome not by telling you whether it is heads or tails or one, two, three, four, five, or six, but I'm going to convey it to you using a certain number of bits. How many ever bits you want, but the minimum number of bits that is needed to tell you the outcome of the experiment. So let's say that I toss a fair coin. Okay. How many bits do I need to tell you the outcome of this experiment of tossing a fair coin?
One.
Good. So one bit. So what I can do is we're going to decide beforehand that if the outcome of the toss is a head, then I'll send you bit zero. I'll encode it using bit zero. If it's a tail, then I encode it using bit one. Okay, so one bit is sufficient to tell you the outcome of the toss of a fair coin. Is this notion clear to everyone, or are there any questions? Okay. So now let's take the roll of a fair die. Now there are 6 outcomes, right? There are 6 outcomes, and I need to represent these using bits. Okay, I need to send a certain number of bits from which you will know what the answer is. So what is the number of bits that I would need to tell you the outcome of the roll of a fair die?
3 bits.
3 bits. Okay, very good. So maybe if it's a 1, then I encoded, I send 3 bits, 000, 2 using 001, 3 using 010, and so on. So 6, I guess, would be whatever, 101. Okay, so these 3 bits, so I send you 3 bits. So if I roll a die and I get a 3, then I send bits 010 to you. You read the bits 010, and then you decide, okay, this is the outcome is actually a 3. Okay, so in some sense, now if I say the information content is the number of bits I need in order to tell you the outcome of a particular experiment, then now if this is how I measure information, if I say that the amount of information involved in a random experiment is the minimum number of bits I need to tell you the outcome of the experiment, then now which one do you think is more informative? If I use this particular definition of information, then now which one do you think is more informative? Is it tossing a fair coin, or is it rolling a fair die?
It's rolling a fair die.
Correct. So it's rolling a fair die, right? So again, this is because I've defined information in a very specific way, and in fact, it is this specific definition of information that we will be using for this course. So it's the minimum number of bits needed to tell you the outcome of a random experiment. Okay, and we see that in these 2 cases, tossing of a fair coin requires less information to be conveyed than rolling a fair die. Okay, any questions so far? Okay, good. So now let's look at another experiment. So I look outside the window and I see that it's pretty sunny. And so I want to know whether it's going to rain today at any point of time today. Okay, so at the end of the day, of course, I'll know whether it rained or not. But now I know that, well, it's sunny outside, I don't see any clouds. So the probability that it's going to rain today is pretty small, right? So there's very low chance that it will rain today. So now, how many bits do I need to sort of tell you the outcome of this particular experiment, whether it rained today or not?
Sir, it depends on how many parameters we are considering to decide.
Okay, so but ultimately, I just want to know whether it rains or not, not
One
the
bit.
additional information. That's just the outcome of this, whether it rains or not.
1 bit.
1 bit, right? There are only 2 outcomes: either it rained today or it did not rain today. So 2 outcomes. So 1 bit in some sense is sufficient. But I know that, well, we have pretty good weather, so it's very unlikely that it's going to rain. So at the end of the day, if I told you that it didn't rain today, then of course you're getting some information, but then it was something that you knew already. You knew that it was very likely that it wouldn't rain today, right? So compare this with tossing of a fair coin, right? So when you toss a fair coin, again you're getting 1 bit of information, right? But then if I tell you that it didn't rain today, you're getting 1 bit of information. But do you think the 2 are in some sense the same? Do you think you've got more information in one case than the other?
Sir,
Yes.
okay. Like in case it's a rain today means if I'm considering like a particular day,
Correct.
if I consider every hour, it's like every hour is like one trial of the experiment kind of thing.
Yeah, you just look at the whole day. Okay, if it rained at any point in that particular day, it's yes. Let's just take today. Okay, so if it rains at any point today, it's a yes. It's one, that whatever bit one. If it did not rain the whole day, it is zero. That's the only thing that I'm interested in.
But both are one bit. But tossing a fair coin,
Uh-huh.
there are like we feel this equal probability of getting the two.
Okay.
Okay, rain. I don't know if there are like equal chances of getting or not.
Yeah, so let's look at it today, right? It's pretty sunny today, so it's very unlikely that it will rain. But still, it's not zero, right? The probability that it will rain today.
Okay, but once we know it's sunny,
Yeah, we know that it is sunny.
obvious. It becomes quite obvious that it will rain, and so the information is little lesser.
Correct. So it's a little lesser. So let's try to sort of develop intuition for this. So you felt that probably that if I told you that it didn't rain today, you're getting less information because it's already pretty sunny at this point. We have good weather, and according to the prediction, it's not going to rain today. But on the other hand, tossing a fair coin, you somehow felt that when you see the outcome, you're getting some more information. So one way to think about it is the following. Let's say that I wanted to guess what the outcome is going to be, right? It's easier to guess the outcome of whether it's going to rain today than it is to guess the outcome of tossing of a fair coin, right? So if I try to guess the outcome of a fair coin, there's a 50-50% chance that I'm going to go wrong, right? Whereas I know that it's sunny today, so if I had to guess whether it is going to rain today, I'm going to say no, it's not going to rain, and with very high probability, I'm going to be correct. Right? So in some sense, if it's harder to guess, then on seeing the outcome, on getting the outcome of that particular event, in some sense, you're getting more information. Right? But on the other hand, if it's very hard to guess that particular outcome correctly, then it's less likely. Then it means that in some sense you're getting more information out of it. Does that make sense? Any questions? Okay, so let us say that I have a random experiment, and let's assume that there are m possible outcomes of this random experiment. So in the case of tossing of a fair coin, there are two possible outcomes, 0 or 1. In the case of rolling of a fair die, there are 6 possible outcomes. So similarly, if I had, say, a 22-sided die and I rolled it, then it has 22 possible outcomes, and so on. Right? So let's assume that I have some experiment where there are m possible outcomes. These outcomes may be equally likely, they may not be equally likely, it doesn't matter, but there are m outcomes. So if I had to somehow convey the outcome of this experiment to you using bits, then how many bits would I need to convey to you the outcome of this experiment?
Log m. Upper bound of log m.
Yeah, so it's a seal of log m, right? So the number of bits required would be the seal of log m. What is the base of the logarithm?
2.
So 2.
Yes, good. So I need the seal of log m, by which I mean that it is the smallest integer which is greater than or equal to log m. Okay, so I need log m bits in order to tell you what the outcome of this experiment is.
So this is for a die?
No, this is for any experiment which has m outcomes.
Okay.
So take any experiment where the number of outcomes is m, then the number of bits I need to represent any of the possible outcomes is log m bits. Right? So if I'm using, say, k bits, so if I'm representing the outcome of any experiment using k bits, then it means that the number of outcomes, what can you say about the number of outcomes?
2 to the power k.
Yeah, so it may be 2 to the power k or slightly less than 2 to the power k. Right? So you know that the total number of outcomes is at most 2 to the power k. Okay, good. So now let's again come back to tossing a coin. Okay. Now if I toss a fair coin, then it's equally likely that it's a head or a tail. So let's assume that tossing a fair coin, the amount of information that you get by tossing a fair coin once is 1 bit. Okay. Now, if I have a slightly bent coin where the probability of a head is larger, okay, the probability head is, let's say, a 0.9. So with 0.9 probability, when I toss a coin, I'm going to get head. With 0.1 probability, I get a tail. Okay. So in this case, at least we have. So do you think you're getting the same amount of it? So I toss the coin, and then I tell you the outcome, right? So how much information do you think you're getting? So again, going by this very intuitive notion, do you think you've got 1 bit of information or something slightly less than 1 bit of information? What do you think? Again, you can take a wild guess, doesn't matter.
It should be lesser information.
Okay, so one guess is that the amount of information that this gives you is less than 1 bit. We will make things more formal. We'll see why this is the case. But well, if you just had to say the outcome of a fair coin, you actually need 1 bit to convey the outcome. But we'll see that the amount of information content in this particular experiment is less than 1 bit. But anyway, we'll look at this as we go along. So now we have some at least intuitive notion of what it means by information. The fact that information can be measured, right? So in some sense, it is how many bits I need to convey in order to tell you the outcome of random experiment. Okay, let's think of that as the information content of random experiment or of a system. Okay. So we'll explore these ideas of information and what it means to store information, to transmit information, and how much information you get by estimating or communicating across a medium, right? So in this particular course, we'll explore 3 problems, and these 3 problems will be connected to are sort of related to communications, broadly speaking, but at the same time communications or estimation. But we'll look at these 3 specific problems. So information theory deals with many other problems as well, but these are 3 problems that that information theory started out with. So that is what we will explore in some detail. So the first is of course data compression, and we'll use data compression to formalize the notion of information content of a system. Okay, so the data compression problem is the following. Let us say that I have a file which consists of n bytes. Right, I have a file. I have an n byte file. I need to compress it. So let's say I have a text file or an image. I want to compress it down to say k bytes, where k is as small as possible. Okay, so I want k to be much smaller than n. Okay, so the question is, now given an n byte file, how small can k be? Let's say I have a text file which is which is maybe a 1 GB text file. I want to compress it. Can I compress it down to 1 megabyte? Can I compress it down to 1 kilobyte? Or is there a limit as to how small I can make it? Right? So that is what we will explore in the problem of data compression. So let us define this quantity, which is k over n. So obviously, if you have a larger file to begin with, obviously k will be larger. That's intuitive. And if it's a smaller file, then hopefully k will also be smaller, right? So if you want to compress a 1 gigabyte file, then the compressed file will be something maybe 100 megabytes. But then if I am trying to compress a 1 megabyte file, obviously the compressed file size will be much smaller than 1 megabyte. Right, so let's look at this quantity, which is the compressed file size. So the compressed file size, and this is the original file size. All right. So if I look at this ratio of the compressed file size to the original file size, this is a quantity that I will call the rate of the compression. So if I call this the rate, then how small can the rate be for let's say text files? Okay, we'll see that there's a limit to this. You can't make it arbitrarily small, and that's governed by a fundamental quantity called the entropy. But the data compression problem is basically this. So given an n byte file, how small can the compressed file be? How small can you make the rate of compression for a given, let's say, class of files? Okay, so that's one problem that we look at. The other problem is which is something called the dual of the data compression problem. So let's assume that I have a k byte file. Okay. Let's say I have a k byte audio file. Okay. And I want to transmit it across a noisy medium. Let's look at cellular communication. So I have a cell phone. I want to talk to someone else, or I want to upload maybe a picture of mine to WhatsApp or Instagram or something else. So I have a file that I want to upload onto the internet, and I'm using my phone to do that. Now the link between my phone to the cell tower, or the base station as it is sometimes called, it's a noisy medium, right? There's a lot of noise in this system. So, but still, but still, miraculously, we're still able to upload files, download files, talk on the phone, as though there's absolutely no noise. So when you're uploading a file, you know that file is going to be exactly stored on the internet, and the next time you try to download it from the internet, you're getting it back exactly the same thing. You're getting an exact copy of what you had uploaded in the first place, right? And it's essentially error-free, despite the fact that you're communicating over a noisy medium. Right? So the question is, how do you communicate reliably across a noisy medium? So one way to do it is to sort of introduce some sort of redundancy. You convert your n byte file, you somehow encode it in some fashion to maybe n bytes, so k bytes to n bytes. You encode, and then transmit it across the channel, which is say the wireless channel. So obviously, the larger n is, maybe you're repeating the same thing. You're sending it again and again, so that eventually the receiver is able to decode correctly. So how small can, again, now I have this notion of rate, which let us say I define it as k over n. So how large can the rate be? Right. So in other words, if I'm using the channel n times, or if I'm actually sending n packets across the channel, then how much useful information can I send in n packets? So obviously I need to introduce some amount of redundancy intuitively, but what is the minimum amount of redundancy that I need to include so that my receiver is able to get it correctly? Right? So that's the problem of communication over a noisy medium. The third problem is what I call binary classification or a hypothesis
Sir?
testing problem. Yes.
Sir, k byte is the actual size and n is after adding
Exactly, after adding
density.
redundancy.
Oh, okay, okay.
Anyway, I mean, it doesn't particularly matter now. I could take my metric to be n over k or k over n, whatever. But we'll see that we'll define it as k over n just for historical reasons. Okay. The third problem that we look at is classification. So let's say that I want to design a spam filter for my email. So whenever I get an email, it's either going to be spam or not spam. But I want my spam filter to correctly classify as much as possible. So obviously it'll make an error some of the time. It won't be correct all the time. And I want to minimize this probability, right? So how do I design a spam filter? Let's assume that I want, of course, I can't have 100% accuracy all the time. So if it is correctly spam, if it is actually a spam, then I want it to correctly categorize it as spam. And at the same time, if it is not spam, then I don't want it to incorrectly categorize as spam. So there are two sort of bad events that can happen. And it turns out that you can't make the classification error of both to be zero. There seems to be a trade-off between the two. And we'll see that given that I want to have a false positive, if I want to maintain a certain probability of error of false positive, what is the smallest probability of false negative that we can achieve? Okay. So these are three problems, concrete problems that we look at to motivate information theory. And we'll see that tied to each of these three problems, there's a fundamental quantity. So tied to the data compression problem, we'll see a quantity called the entropy. I'll define the entropy, we'll see properties of this entropy, it's a function. And for communication, we'll see a quantity called the mutual information. It tells you how much redundancy needs to be added, or what is the minimum, what is the maximum rate or maximum amount of useful information you can transmit across a noisy channel. When it comes to binary classification, we'll see a quantity called the KL divergence, which tells you what is the least probability of error that you can have. So we'll see each of these. So in some sense, this course is about these three problems, but also it is about these three quantities: entropy, mutual information, and KL divergence. And we'll see the relationship between these three quantities and properties of these three quantities. All right. So from the next class onwards, we'll start with data compression, very briefly go through data compression, communication, and binary classification. But since I have a few more minutes to go, let's run a simple experiment. Okay. So my claim or my hypothesis is that data compression in some sense should give you a measure of information. And to see that, let's do a simple experiment. Right? So here with me, I have a bunch of text files. Okay, all these three text files are basically some classic books. So let's see, the first file turns out to be Great Expectations by Charles Dickens. So this is one book. It is a 1 megabyte file. Okay, it's a 1 megabyte file. The second book turns out to be Little Women by Louisa May Alcott. And similarly, so I have a bunch of classic books. They're all of different file sizes. So one is 1 megabyte. The second is also second one is 3.2 megabytes, 862 kilobytes, and so on. So let me try to compress each of these files and try to compute this quantity, the rate that I had defined. All right. So sorry. Yeah. So K over N. So you have K, the original file size. Sorry. Let's try to compute the ratio of the compressed file size to the original file size. All right. So the only common feature among all of these files is that they're all English. They're all in English. There are some special characters here and there, but most of it is valid English words. But they're completely different books, right? You can do this, run this experiment on your own as well. Try to experiment with it. Take a bunch of books, all of which should be at least roughly a megabyte or so. So I'll try to compress this. Okay, I compress it. Let's say I zip the file. So this is a 1 megabyte file. The compressed file size turns out to be 386.7 kilobytes. Okay. So this is for Great Expectations. It is 386.7 divided by, this is 386 kilobytes by 1000 kilobytes, which is 0.3867. So this is the ratio of the compressed file size to the original file size. Okay, so I compress the next book. So this is a so this is also a 1 megabyte file, and the compressed file size is 399.6 kilobytes. Okay, so roughly the same. So 399.6 kilobytes divided by 1000 kilobytes, that's 0.3996. So roughly the same. I take another book and I try to compress. Okay, so this is 3.2 megabytes, so roughly, so 3359 kilobytes, and the compressed file size is 1.2 megabytes. So let's see, 1220 divided by 3359. It's a 0.36. Okay. Similarly, I go on. This is 862 kilobytes. I compress. So 327 by 862. Right. So we see that no matter which file I compress, these are all books by different authors, but the compression ratio roughly is the same. Right. The only common feature is that these are English books. All right. So in fact, we'll see that this quantity, it's not exactly this, but if you take any large text file, English text file, it has to be a valid novel and it has to be in, let's say, text format. The rate of compression with, say, zip is always going to give you something around the same thing. So it's going to be between 0.36 and 0.38. And it turns out that this is a striking feature of English text. And this, in fact, if you take an even larger file, maybe a 1 gigabyte text file, it's going to be slightly lower. It's going to be around 0.3 or so, because we're now dealing with small text files. But that turns out to be what is called the entropy of the English language. So there is a fundamental limit. And in some sense, this is the amount of information, whatever that means, the amount of information which is contained in 1000 megabytes of English text. So in 1 megabyte of English text, you have roughly 386 kilobytes of useful information, whatever that means. All right. So any questions so far?
Sir,
Yes, Deepak.
yeah. So I have a question regarding a bit related to admin stuff.
Sure.
So sorry, I joined the class a bit late because of the previous class. So I just wanted to know, sir, I am attending this course online because I am an external PhD student. Will it
Okay.
be possible for me to credit this course, like in terms of exams and all? Because I cannot come to the campus, sir.
I see. Okay. So I'll just check with the account section as well as to what can be done. But in principle, I think it should be okay. Is it possible to at least come for the final exam?
So that also, because right now I am in Haryana, so and my job is although in Hyderabad, but we are working in work from home fashion.
Okay, we can try to explore something.
Okay, so because the course drop deadline is, I guess, this week only. Although I have added the course in my like the AIMS portal.
Sure.
I just wanted to check with the exams. So
Sure.
please, if you.
So will you be uploading the syllabus of the course in the classroom?
So it is, as I mentioned, it is on the course webpage.
Okay.
You can, I'll put a link to this in Google Classroom, but this is where most of the content will be present. So you can get the references, syllabus, rough schedule, all over here. I'll also be uploading notes and other material here.
So I come from AI background. So only the probability and random variable is the prerequisite here, correct?
Yes, yes.
I don't need anything from the electrical background.
You do not need anything from the electrical background. If you've taken a course in digital communication, it is helpful just as motivation, but there are absolutely no other prerequisites.
Okay, sir. Thank you, sir.
Hello, sir.
Yes, Manish.
Yesterday I talked to you, right?
Yeah, so we can discuss that after this, if that's okay with you. Any other questions? Sure. So I will upload the recording of today's class. Any other questions? Okay, so we'll have online class tomorrow as well, but from Monday onwards, it will be in person. So please do note that attendance is mandatory for both online or offline. Okay, so if there are no further questions, we'll see you all tomorrow. If you have any other questions at any point of time, you can just post it in Google Classroom. Let's try to keep that as interactive as well. But of course, you can also ask me in the next class. All right, or if you have any other questions, you can also send me an email. Okay then, so see you all tomorrow.
Thank you, sir.
Thank you.